area, conjugate beams, or whatever. Yeah. So no problem. You can get that and this. No problems. And then use that to calculate By. So basically, you do 2 displacement calculations. 1, 2. For 1 redundancy. Now, it's not unique. Of course, you can choose other redundant force. So for instance, you can choose the bending moment there as your redundant force. So you first remove that redundant force. So calculate the effects of the external force, and then remove that external force, apply the redundant force backward. So this is removing the redundant force. So if you remove M, then it becomes simply support. And you calculate rotation angle. Then you remove the loading, apply back the bending moment. You can calculate the rotation angle as well. Of course, you assume that bending moment is equal to 1. So then you have this flexibility coefficients, and then compatibility equations. Again, there's a plus and minus for the deformations that you calculated. So you have to fix a plus directions, and so some of these will be positive, some of these will be negative. Good? Clear? So let's see. This is hinge, roller, roller. So 1 degree indeterminacy. So you need to choose 1 redundant force. So remove that redundant force. So I choose By as my redundant force. Remove that redundant force. Calculate the displacement corresponding to that redundant force under actual loadings. And then apply the redundant force with a magnitude of 1. Calculate the displacement again. And then put into the so-called compatibility equations. So that equations, the only unknown is the reaction force, or redundant force, By. And again, it's not unique. You can choose this as a redundant, or you can choose that as a redundant. It doesn't really matter. As long as you find the right one that can simplify your calculations. It's up to you. But once one of the force is found, then the structure becomes determinate, right? So everything, the rest of the analysis is simply just an equilibrium analysis. Oh, you received some text from your friend? Huh? How come you know? No? Oh, okay. All right. Okay, so this is a concept. Don't try to memorize. Memorizing doesn't really help. So you need to know the concept. Concept is very important than memorizing. So here is a truss structure. The structure itself is a determinant, but the support conditions are not determinant. So you have a hinge and a hinge there. And also have a horizontal force, vertical force. So this is 1 degree indeterminate structures. So you identify a redundant force. You have a choice to have this, that, or this and that. So let's say I choose dx as my redundant force. So removing dx means that you are translating the hinge conditions to a rolling conditions. Because dx has to be removed, no horizontal force there. So that is a roller support. So the whole structure is a determinate structure analysis. And then you need to calculate the deformations along that directions. And next, you remove all the external force, apply a unit force acting along that directions. And compatibility equations goes like that. So basically, just forcing the displacements of D back to the original positions. So this is the idea of compatibility equations. Forcing the deformations of the point back to the original position. Is that clear? Good? All right, so we can also use this concept to solve some structure like this. This is reverse of the previous example. This is support-wise is determinant, but the structure itself is 1 degree indeterminacy. So truss, diagonal, diagonal, 2 diagonals, 1 too many. So this is 1 degree indeterminate structure. So you can choose, you need to choose one redundant force. Now, that redundant force cannot be from the support because the support is themselves, they are determinant. So you cannot choose the support as your redundancy. So you have to choose the member force as your redundant force. Right? So this is what we can do. You need to remove one component first. You remove one component and apply backward. So how do you remove? Well, you just do a cut there. You just assume that you can cut it open. You cut it open, then these two members, the members there will not take any load. All right? It's as if like you're removing that components from the structure. So you cut the components. So you calculate the openings of that components after you cut. And then you need to apply back the force. Removing external force and apply back that member force. That member force is a redundant force. So you need to apply back that member force. It goes like this side is tensile unit, tensile force, magnitude of 1. The other side is tensile force, units of 1. And then you calculate how much that component overlapped. So this is opening, this is overlapped, and you know that you should have a continuity there. That cross-section is continuous. So you cannot have opening, you cannot have overlapped. So they have to be compatible. So your compatibility equations is exactly the same. All right, so, but this kind of calculation actually is very troublesome. It's quite difficult, actually. So I wouldn't suggest you to use this method on some structures like this. If you have an internal indeterminacies, I wouldn't suggest you to do that. It's too complicated for this method. We have other methods that you can use and solve it very easily. So, but that's the idea. That's the idea you can do. Okay, now how about a two-dimensional, 2 degrees of indeterminacies? Then you need you know that you need to choose 2 redundant forces. 2 redundant forces. So clamp, hinge, 2 redundant forces. Let's say I choose dx and dy. So you need to remove these 2 redundant forces first, keeping the external force, and then calculate the displacement along the 2 redundant force directions. So here, this is the first calculations you need to do. So under the actual loads, removing the redundant forces, calculate displacement vertically and horizontally. And then remove the loading. Start to apply the redundant force one by one. One by one. So you apply the first redundant force, magnitude of 1, and then calculate this and that. Vertical displacement, horizontal displacement. And then you apply vertical redundant force, unit of 1. Calculate vertical displacement, horizontal displacement. So eventually, the compatibility equations goes like this. You have 2 unknowns, dx and dy, and these are the flexibility coefficients that you calculated. You need to calculate 4 flexibility coefficients plus 2 displacement under actual loading conditions. So there are a total of 6 deformation calculations you need to perform for, oh, somebody actually informed you, right? No? Oh, okay. Good morning. We are almost done. Okay, so simultaneous equations, dx, dy, you can solve them. But before solving that, you need to solve 6 deformations. Oh, it's quite a lot of work, isn't it? Quite a lot of work. Now, I can use the same concept to analyze the effects of settlements. So let's say I have structures like that. This is 2-degree indeterminate structures. Under loading of W, distributed loads, and on top of that, B and C supports have settlements. They settled downward. So settlement itself will create forces, will introduce forces into the structures. So how do we analyze that? So following the same concepts, I want to use compatibilities. So first, I need to choose redundant forces. I need to choose 2 because this is 2-degree indeterminacy. So I choose B and C as my redundant force. So I remove these 2 forces and have the external force acting on the structures. So removing the reaction forces there is equivalent to removing the support. So this is the first analysis I need to do. And I calculate the displacement at B and C under the actual loads. And then I start to add back the redundant force. So there are 2 redundant forces. I do it one by one. By, I apply a unit force along the by directions. So that gives me the flexibility coefficients there. And then the second redundant force is along cy directions, unit force. And I calculate flexibility coefficients and flexibility coefficients. And superimpose all 3 of them, multiplying the unknown redundant force respectively. Gee, it doesn't work. You know, people just, some of you are spies sending out message to your friends. Huh? What do you say? Don't count them. Oh, this is a bad classmates. Yeah. 小聲，講俾我聽，唔好太大聲。Okay, all right. So that is the compatibility equations. Now, settlements. The effects of settlements is you're not going to push the deformations back to the original positions. So the original position will be settled down to a new positions. So the compatibility equations, when you add things up, you should reflect that the final position is not the same as the original positions. So you should put the final positions there, which then accounts for the settlements. And again, there's a plus and minus issue involved, so be careful. So everything goes up, positive, goes down, negative. So plus and minus issues become very important. So that's compatibility for settlements. Now, for settlements like this, the whole structure settled, not only some of the support settles. So if the whole structure settles, so then you need to distinguish the settlements into 2 categories. One is called rigid body settlements, and the other is flexible body settlements. So what is a rigid body settlement? Now, rigid body settlement is the structures like that I just completely settle without any deformations. So this kind of settlements does not introduce any forces into your structures. So if the structure is like that, and then you settle in a straight line fashion, then you don't see any force from the support because it's a rigid body. No curvature, no bending moment, no shear force, nothing developed in the structures, right? So it's fine. If the structures just settle like that, no worry, you don't see anything. So when the structure, the support have differential settlements, which leads to non-rigid body settlement, then those kind of settlements will introduce additional reactions or forces into your structures. So anyway, so what you can do is you do analysis removing the redundant forces and then add them back one by one. So for this case, there's no external force, so no external force contributions. So you just have to do one redundant force analysis, and then second redundant force analysis, and then put it into a compatibility, enforcing final compatibility conditions to reflect that you only account for the settlements measuring from the rigid body positions. So that is the final settlements that you put into the right-hand side, and that is that put in there. You don't take the whole settlements and put it in, right? Because the real settlements actually compose of the rigid body settlements plus the flexible body settlements. And we say that this rigid body settlement does not contribute to any force into your structures. Okay? So is that all right? So this is the first approach that we introduced, called compatibility approach. Now, I will use the remaining time to give you two examples. All right, very simple one here, illustrating the, give you the real numbers so that you can make sure that you can operate this. So I'm going to use the compatibility equations. So here is a By. I'm going to choose as my redundant force. So I'm going to do two analyses. First is removing the redundant force. Oops. Removing the redundant force, having this force there, and calculate this delta B. So I want to use Castigliano theories to do that. So I use Castigliano. So this is what I need to do. I need to put a corresponding force there. I call it F. So I want to do this. Delta B is wrong U, wrong F. And after I have taken the derivative, I set the force equal to 0. So I need to have the expressions for the strain energy. So the bending moments there is, if I assume measuring x from there. So this is minus fx. And the bending moment there is minus fx minus 50x minus 6. So the strain energy expression is 0 to 6 minus fx squared 2ei dx, and then integrate from 6 to 12 fx plus 50x minus 6 squared 2ei dx. That's the strain energy expressions. So I just take that, put it in. So this is 0 to 6 fx squared ei dx and 12 fx 50x minus 6 ei dx. Okay, so after I taking a derivative, then I just substitute f equal to 0 because f is fictitious, imaginary. Okay, then integrate it out. So this is 9,000 ei. So that's the first analysis. That gives me this value. The second analysis will be having a redundant force only, no external force, just the redundant force. But redundant force itself is an unknown. We don't know the redundant force, so I apply a redundant force of 1. You're coming to make sure that I dismiss. Okay, so I can do that. I assume a fictitious force of F. F eventually is equal to 1. It's not equal to 0. So I do an analysis using a Castigliano theory. So I'm going to obtain this flexibility coefficients FBB. So this FBB is wrong U, wrong F, but now F should be equal to 1. So strain energy is 0 to 12 fx squared 2ei dx. So you take this strain energy expression, substitute in. So this is integrations 0 to 12 fx squared ei dx. And then you let f equal to 1. So this gives you 576 ei. Okay, so this is positive. This is downward. 9,000 over EI. Same direction as F, so it's downward. So that one is negative. So compatibility conditions is minus 9,000 over EI. And this is upward, positive, so it's a positive. So that's our compatibility equations. Do you have any question? Is differentiated with respect to F. Okay, so By then can be found. There we go. So once By is found, once this is obtained, then the other force can be obtained through simply just equilibriums. So these two just obtained from equilibriums. Okay, good. Now I show you a settlement problem. So sign-up sheet is here. Who has the final sign-up sheets? Can I have it? You two are from the civil class visits. We don't have too many students here. You want to do it next time? I only have about 1/3 of the student here. Never mind. You want to do it still? Or next time? You still want to do it? Still want to do it? Okay. So yeah, I promise to give the civil society sometimes for them to promote. How come you always use my time? How come you're not using a geologist's time? They'll have a midterm exam tonight, so you better go there. You make sure that they are all here. All right. So let me, before I pass it to you, my policy is I don't take attendance. I say it in the first class. I don't like to take attendance. So this kind of records is only helping you to either goes up or go down. Okay? If you are at the boundary of value, I'll see the records. Or I cannot decide whether I need to give you an A or give you a B. Then I take a look at these records. Okay? It's not the dominating factors. It's just a so-called compassionate factor. Okay? So with that, maybe pass on to civil structure society. Right. Thanks. You can use that.
Okay, we'll use the computer.
You can use a computer. Sure.
咁我哋就係師傅 Year 2嘅實習啦。